Welcome to AI Peer Review. Today, we're digging into a really interesting paper called Grounding DINO, Marrying DINO with Grounded Pre-training for Open Set Object Detection.
Yeah, this one's pretty cool. It's all about tackling a big challenge.
Yeah.
How do we get AI to detect basically any object you can describe using language?
Exactly. Not just the categories it was trained on. It feels like a really important step towards more general AI vision.
Totally. So in this deep dive, we're going to unpack how grounding DINO pulls this off. We'll look at how it builds on older models but brings in ideas from grounded pre-training and transformers.
Right. The goal is to figure out what the key innovations are, what makes it good at this open set stuff, and, how it stacks up against what came before.
Let's get into it.
Okay, so let's start with the problem itself. The paper kicks off contrasting closed set and open set detection. Figure 1A and B illustrate this. Can you briefly explain that difference and why open set is such a big deal?
Sure. So closed set detection, that's the traditional approach, right? You train a model on, say, pictures of cats, dogs, cars, a fixed list, and it can only find those things.
The predefined categories.
Exactly. But the real world, it's messy. It has tons of stuff the model hasn't seen. Open set detection tries to handle that. The idea is to detect objects based on a text description, even if it's a completely new category.
Like in Figure 1B, where it shows detecting a World Cup or a lion, things maybe not in the standard training data.
Precisely. That's the challenge.
Yeah.
Getting the model to understand language descriptions and connect them to visual features for objects it's never been explicitly trained to recognize.
Yeah.
Traditional models just can't do that. They're locked into their training set.
Okay, so grounding DINO comes along to tackle this. What's the core idea? How does it manage this open set capability?
Well, the name kind of gives it away, grounding DINO. They take the DINO object detector, which is already pretty solid,
Right.
and they enhance it, basically teach it how to ground language descriptions in the visual data. And they make a point of saying, open set, open world, open vocabulary. They're treating these as essentially the same task.
So it's about fusing a strong detector with this language grounding ability.
Exactly. It's moving beyond just matching visual patterns to fixed labels, and instead learning to link visual details to potentially any description you give it.
The paper talks quite a bit about increasing feature fusion. Figure 2 shows this visually. Can you walk us through why that's important and where this fusion happens?
Yeah, Figure 2 gives that high-level view. You've got the backbone extracting initial features, the neck refining them, and the head making predictions. The authors argue that you can, and maybe should, mix the image and text information at multiple points.
Okay.
They mentioned 3 stages. Stage A is in the neck, fusing early on. Stage B is about making the queries, the things that look for objects, language aware from the start. And stage C is deeper fusion within the head itself, like in the transformer decoder layers.
And the idea is more fusion equals better alignment.
That's the claim. More interaction points between image and text features should lead to a better joint understanding, which is crucial for finding objects based only on text descriptions.
Now, grounded pre-training seems central to this. Why is that specific approach so important for zero-shot transfer, especially compared to just using something like CLIP?
Ah, right. That's a key point. So lots of earlier methods used CLIP, which learns connections between whole images and captions. It's good for general understanding. But object detection needs something more fine-grained. You need to link specific regions in the image to specific words or phrases. Region CLIP actually pointed out this limitation with standard CLIP training.
I see. It's about region-level understanding, not just the whole image.
Exactly. Grounded pre-training, used by models like GLIP, trains directly on data that explicitly links image regions to text phrases. It learns that grounding task directly. Grounding DINO takes that approach and refines it.
How does it refine it? You mentioned sub-sentence level text features shown in Figure 4. What's that about?
Right, Figure 4 shows this. So imagine you have an image with a cat, a dog, and a bird. A simple way is just feed the text cat, dog, bird into the model.
Okay.
But the problem is, during text processing, the features for cat might accidentally get mixed up with features for bird through self-attention, even if they're totally separate objects in the image.
Ah, unwanted interference.
Yeah. So the sub-sentence approach, shown in 4B, uses attention masks. Think of it like keeping the text processing for each potential object category mostly separate. It stops the text features for unrelated objects from influencing each other too much.
So cleaner text features for each potential object.
Pretty much. It leads to better, more focused grounding between the right words and the right visual parts. Helps a lot when you have multiple different things you're looking for.
Makes sense. Okay, let's dive into the architecture components. First up, language-guided query selection. What does this part do? Maybe equation 1 or algorithm 1 helps here.
Yeah, this module is about efficiency. It's trying to pick out the most promising image regions before the main decoding happens, using the text as a guide.
How does it do that?
Equation 1 shows the core calculation. It basically computes a similarity like a dot product or cosine similarity between all the image features and all the text features.
Finding the best matches.
Right. For each image feature, it finds its maximum similarity score across all the text features. This tells you how strongly that image part relates to any part of the input text. Then algorithm 1 just says, okay, pick the top NQ image features, the ones with the highest scores, and use those to start the decoding process.
So it focuses the decoder on relevant areas.
Exactly. And they mention using mixed query selection too, which combines this language-guided stuff with positional information like dynamic anchor boxes from DINO. So you get both semantic and spatial guidance.
Okay, then there's a cross-modality decoder. Figures 3 and 5 give more detail. How does this bring the image and text info together?
This is really the heart of the fusion process in the transformer. Figure 3 shows it in the pipeline. Figure 5 zooms into a decoder layer. Each layer takes the queries we just talked about, plus the image features and the text features.
And does what with them?
Well, within each layer, the query first does self-attention, refining itself. Then it does cross-attention to the image features, pulling in visual info.
Standard transformer stuff so far.
Right, but here's the key addition for grounding DINO. There's an extra cross-attention layer, where the query attends directly to the text features within each decoder layer.
Ah, so explicit text interaction at every step.
Yes, that's a big difference from the original DINO. By repeatedly letting the queries pull information from both modalities, image, and text, it builds up a much richer, more aligned understanding. Then a feed-forward network processes it, and it goes to the next layer.
Got it. And how is this all trained? What about the loss function?
The loss function combines a few things, borrowing heavily from GLIP, actually. For the bounding boxes, it uses standard stuff, L1 loss and GIOU loss. Pretty typical for DETR-like models.
Okay, for localization, what about classification? Especially for OpenSet.
That's where the contrastive loss comes in, mixed with focal loss. Instead of predicting from a fixed set of classes, the contrastive loss pushes embeddings of the correct image region and text description closer together in feature space.
And pushes wrong pairs apart.
Exactly. It learns a shared space where similar concepts are near each other, regardless of modality. The focal loss helps handle class imbalance, focusing on harder examples.
And there's that bipartite matching step first.
Yep. Standard DETR practice. Use the Hungarian algorithm to find the best match between predictions and ground truth based on both box and classification cost, then calculate the loss on those matched pairs. Plus, they use auxiliary losses after each decoder layer, which helps with training stability.
Okay, let's switch gears to results. The paper boasts some really impressive zero-shot numbers. What did they find on COCO and Odin W? Table 1 seems relevant here.
Yeah, the zero-shot results are pretty striking. On
Yeah.
COCO's zero-shot, they hit 52.5 AP, which is really strong for detecting unseen categories.
52.5, wow.
And on Odin W, which is arguably tougher, they set a new record with a mean AP of 26.1. Table 1 compares it to other methods, and grounding DANOL actually beats even huge models like Florence on Odin W.
That's quite something. This suggests the approach really generalizes well.
It really does. It seems this method of learning the shared embedding space works very well for transferring knowledge to new objects just from text.
What about referring object detection? Tasks like refcoco, refcococo plus ifco. Table 5 shows results there. What does that tell us?
Those results are also really strong. Referring expression tasks are harder than just detecting categories, right? You need to understand descriptions like the small dog to the left of the chair, not just dog.
So understanding attributes, relationships.
Exactly. The good performance on refcoco variants, shown in Table 5, demonstrates the grounding DINO isn't just mapping simple labels. It can handle more complex, descriptive language to pinpoint specific objects, even novel ones with specific attributes.
Interesting. You mentioned figure 8 earlier in relation to this.
Yeah, Figure 8 shows some examples, but also highlights a subtle issue we can maybe circle back to later about annotation differences. But fundamentally, the refcoco's results show good language grounding.
Okay. And the ablation studies in Table 7. Did they confirm that the different architectural choices actually help?
They did. The ablations are pretty clear. Adding encoder fusion, for instance, gave a nice boost, supporting their idea about fusing features early.
What else stood out?
The language-guided query selection, the text cross-attention in the decoder, and the subsentence text prompting, they all showed positive impact. especially on the LVIS dataset and for zero-shot COCO. It confirms these components are doing useful work, particularly for the harder open set or large vocabulary scenarios.
Good to see the components validated. What about efficiency? Is this a huge, slow model? Table 20 has a comparison with GLIP.
That's actually a good point. Table 20 shows that grounding DINO T, the smaller one, has fewer parameters than GLEOPT and is actually faster at inference.
Oh, interesting. So better performance and potentially more efficient?
Seems like it, at least for that variant comparison. That's definitely a plus for practical deployment. It means it's not necessarily trading off all efficiency for capability.
And one more experimental point. Training from scratch versus using pre-trained DINO weights. Table 10 and Figure 10 touch on this.
Right. The takeaway there is pretty straightforward. Initializing with pre-trained DINO weights makes the model converge much faster during training.
As you might expect. Yeah.
Exactly. You might end up at similar performance eventually either way, but starting with pre-trained weights saves a lot of training time and compute. It's the practical way to go.
Okay, beyond the numbers, they show some cool applications like image editing in Figure 1C and Figure 9 and grounded generation in Figure 10. How does grounding DINO enable those?
This is where the language understanding really shines. For image editing, like in Figure 9, you basically use grounding DINO first to find an object based on text, say the red car.
Okay, it gives you a mask for it.
Right. Then you feed that mask, along with a new prompt, like a blue bicycle, into an in-painting model like Stable Diffusion. And it replaces the car with a bike in the right spot.
Very cool. And the geology integration in Figure 10.
That allows even finer control.
Yeah.
Grounding DINO provides the bounding box based on a phrase, and then GLGene can generate or modify something specifically within that box according to the prompt. So you could say, put a cat here, and point with a box derived from text.
So it enables really precise, language-driven image manipulation.
Yeah, it opens up a lot of creative possibilities.
Now, you hinted at a limitation earlier regarding Figure 8 and RefCookio annotations. Can you expand on that?
Yes, it's a subtle but interesting point. The issue is how datasets are annotated. In RefCoco, if the description is, say, the bird, but there are 3 birds, the dataset usually only labels one of them.
Okay.
But grounding DINO, trained on grounded data where every instance matching a description might be labeled, will likely try to detect all 3 birds.
Ah, so it finds everything matching the description, but the benchmark only expects one match.
Exactly. So it might look like lower performance on the benchmark, even though the model is arguably doing the right thing based on its training and the text prompt. It just shows how evaluation metrics can be tricky when training data and test annotations don't perfectly align in their philosophy.
That's a really important nuance. So, wrapping up, grounding denial feels like a pretty significant advance in open set detection. This combination of grounded pre-training with a strong transformer detector seems really powerful.
Absolutely. Its ability to detect things just based on free-form language.
Yeah.
It opens up so many doors. We talked about image editing, but think about robotics, human-computer interaction. Lots of potential.
And the paper itself, with all the analysis and ablations, gives a lot of good insights for researchers. The zero-shot results and the referring expression performance really highlight how robust it is.
Definitely. It's a solid piece of work showing the power of combining these different techniques.
It really makes you think, doesn't it? If you have a system that can see and understand arbitrary descriptions, what new kinds of interactions or applications become possible? What happens when AI truly starts to see the world through the lens of language? That's something to ponder.
A very interesting question indeed. Lots more to explore there.